Hello, let's talk about basics of OSPF version 2. As you guys know, OSPF is one of the example of link state protocols. So, you already talked about the RIP version 2. RIP version 2 or RIP protocol is a distant vector protocol. We have two categories. When it comes to routing protocols. So OSPF is link state protocol, which is very different from a RIP version 2 or distant vector protocol. So in terms of distant vector protocol, it just like also called routing by rumor. That means that, for example, a router that is enabled with RIP, for example, you just listen to the rumor and then just add a one hop based on the rumor and send it out, right? So just RIP or distant vector protocol does not have the whole picture, whole graph of the entire network. It's just routing by rumor, kind of like look at the sign on the road and just go with the sign's direction. So link state protocol, in contrast, has a graph, has the whole picture of the entire network. That means that each router, initially, each router originate the information about itself. So to create some of the link state RSA or some information, then they exchange those information that finally the information is passed around the whole entire network. Or you can say that all the information propagate through the network. So every router has identical information of the whole network. And then based on this identical information or like database, I just obtain the whole graph. So when it comes to link state operation or OSPF operation specifically, we have 4 steps to complete the whole operations. So the first one is establishment of neighbor adjacencies. So for example, the router has several neighbors in terms of physical links, but they have to achieve or establish the neighbor adjacency based on those physical links to establish the logical adjacent neighbor relationship. So in OSPF we call this adjacency. So that's we have to use a data structure to achieve this step. And later on, we have a link state advertisement, or RSA for short. RSA is kind of like a road update. Just every router just exchanges a link state update or link state advertisement. And then so that everybody just know every RSAs or every link state advertisement. And based on all of the RSAs, they just build a link state interface, databases. So every router has a identical link state database. So by using the identical linked state database, but then they just invoked the SPF algorithm, which is the standard-based short pass uh, algorithm. So to work out a best route for every subnet. Though this is the whole operation. So based on these operations, we have three different and also vital data structures. They are adjacency database to help create a neighbor adjacency relationship. And the second one is a link state database. So all of the RSA link state advertisements will be stored in the link state database. The third one is definitely routing table. That's for a router to forward the traffic or make a routing decision. These are three basic data structure for link state protocol or for OSPF. And when we go deeper into the establishment of OSPF neighbor adjacencies, we can see the whole negotiation process. There are 7 states or 7 transitions we have to go through from the down state initially and to the fully fully achieved or fully established relationship, which is a full state. So this 7 state kind of like they have the state machine and the transition criteria. So if you want to go deeper, you can see some of the books. And also, when we're talking about neighbor relationship establishing, so we use this multicast negotiation protocol, where we use multicast protocol to help establish the whole neighbor relationship. And also we leverage another important one, which is router ID. So just remember that every RSA link state advertisement has the route ID field. So it just kind of like identify or specify or route ID is identification to specify the specific RSA, and also as identification for a OSPF router. So another fact I'm gonna go and highlight is this DR election, or DR means designated router. It only happens on the multi-access network, for example, Ethernet. So let's say here, give you an example. This is a one data link, right? This is a one LAN. This is one LAN. On this line, there are 5 routers. 1, 2, 3, 4, 5 routers. 5 routers are sitting on the same data link. So based on our rules, every OSPF router has to negotiate and establish adjacency with each other. So that means that the final number of the adjacency will be very massive, which is n times n minus 1 divided by 2. So is this necessary? Because the 5 routers sitting on the same database, they might have some overlapping knowledge and updates. So the answer is it's not necessary to have this one-to-one relationship or adjacency. So if we try to simplify this relationship, so just bring in the DR election, this new process. So here we just draw again this 5 router sitting on the same Ethernet or same data link. So by using the DR election, so we just kind of like we elect a leader on this same data link. For example, we call this leader is designated router. We also have to elect a backup DR, backup leader, which is called BDR, backup designated router. So all other routers will be called DR router. So every DR router just only have to have relationship or establish relationship with DR and BDR. So there's no need to have relationship between DR router and another DR router. So that's the simplification of the relationship. So by using this process, we can simplify our topology. Here is a physical topology. We have 3 data link, 1 data link, 2 data links, the third one, the fourth one. But by using this DR on our multi-access network, multi-access data link, we just simplify this topology to a to this this topology. You can see, for example, DEF sitting on the Ethernet, but if D acts as a DR and E acts as a DR router, D and E have some relationship or adjacency. OSPF adjacency, you can see that this kind of simplify the whole topology. So based on this simplified topology, so it just they are exchanging the link state advertisement and just and then to create a link state database. So flooding of the RSA means that after the negotiation, after the adjacency establishment, so these 2 guys just exchange their information, exchange their routing information. So in OSPF, we call this RSA, right? Link state advertisement. So you can see that the flooding of the RSA means that the RSA just propagate through the entire network, through the entire OSPF domain, and make it identical, so that every router just know to achieve or reach to the identical state. This is the flooding of RSA. You can see there's a animation here. So everybody just know the same RSA. You can see that every router originate specific RSAs and propagate the RSA to the entire network. and then just everybody just know the same RSAs. What is RSA? You can see if you show IP OSPF database, you can see there are a lot of RSA. Those are RSAs. So you can see the link ID and advertise router. Advertise router is router ID. So that means who originates this RSA. It's pretty important. Or when you troubleshoot some OSPF issue, and there are a variety of different types of RSA for specific uses. Here I just listed here where I just list these types. So you just care about type 1, 2, 3, 4, 5, which is 5 commonly used one. You have to learn more about each type. For example, the range, the space, the propagation space, and how they originate by some criteria. So those kind of things are pretty detailed. And we also have another one to mention, that the OSPF is a hierarchical protocol. So, and that means that if you look at RIP or distant vector protocol, they don't have like area or hierarchical concept. But with the OSPF or SS, which is another link state protocol, they often has hierarchies. So that means that there are two different hierarchies or structures. If we call it area. So for example, if you're using the single area of the OSPF, so the area number, this is area number 0. 0 is always used for single area. So that means that you put all of the OSPF enable routers into the area 0. That means the whole OSPF domain has only one area. But for multi-area scenario, you can see that there are different areas. We can divide your routers, all of the router, into different areas to make it layered. So for example, you have area 0. They often call area 0 as a BB or backbone area. And I also have area 1 or area this ID. This ID is denoted by a IP address like. Both are okay. The single number or this octet-like area ID are okay to use. And you can see by dividing the all of the devices into different area, and you can see that we just create the flexibility and management domain. For example, we also you might have noticed that there's a particular location or particular role for OSPF enable router. For example, here this guy joined area 0 and area 1 as well. So this guy is called area border router, ABR. So ABR as I said, every router originated its own RSA and propagate to the entire network. But AVR can originate further different types of RSA because, for example, AVR just learn the area ones RSAs or advertisements, and then they just recreate or originate the area one's RSA into the area 0, recreate or reoriginate this behavior is only specific to ABR. So that means that what I'm saying is OSPF has a lot of characteristic and the process operations in detail. If you want to learn more, just refer to some of the relevant books or courses.